Ilqar Cabbarov, Ganja State University, Ganja, Azerbaijan. Title of my talk is On Singularities of Differentiable Maps. In this paper, it is considered the question on the structure of singular points of maps given on real differentiable manifolds. In Marsh theory, the detailed structure of the set of non-degenerate critical points is studied. The results of these investigations apply to studying of topology of manifolds. The structure of the set of degenerate critical points is more complicated. In different areas of mathematics, the main question was the study of manifolds' behavior around the critical points, but in some metric questions of differentiable manifolds, it arises studying of the set of all singular points of maps on differentiable manifolds. Let us introduce the necessary definitions and designations. Let omega be some closed domain of n-dimensional space with smooth boundary. Suppose that in omega it is given some r-dimensional surface by the system of equations with smooth functions fg of x equal to 0, where g takes values from 1 to n minus r, with Jacobi matrix G, which we suppose to have the maximal rank elsewhere in omega. Further, let A0 be another functional matrix region in the transposed view with smooth entries, arranging the elements of the columns of the matrix A0 consequently in a row F11 of X and etc. FR1 of X and so on, FRM of X. Let's take the transposed Jacobi matrix of this system of functions, denoting it as A1. Matrix A1 has the form. Conditionally, we can call this matrix as a first derivative of the matrix A0. Now we repeat the same procedure, that is, arranging the elements of the columns of the matrix A1 consequently in a row. Let's take the transposed Jacobi matrix of this system of functions, denoting it as A2, and so on. Continue this procedure of finding of sequential derivatives since it is not got the matrix AK for given k greater or equal to 1. The matrix defined by such way consists of elements being coincident with partial derivatives of the same order k of the matrix A0 and has the size n multiplied by n in the power k minus 1 Rm, denoting by phi e k the elements of the matrix Ag of X. Let's use the following designations. Lg of X is equal to Euclidean norm of the matrix Ag of X. L is equal to maximum Lg of X, and G is equal minimum Gg of X, where the minimum is taken for the first expression with respect to G and X, and minimum is taken over points of omega. Let W denote the subset of the domain omega in which phi G is equal to determinant of the product matrices Rg to Rg transposed is equal to 0. For G, taking values from 1 to k. The set of singular points we define as a set W being equal to the union of sets Wg. Define now by U the set of solutions of the system first. Below we prove that the set intersection W with U has zero Jordan measure on the surface of solutions. The aim of our work is to prove the following. Theorem: let phi g greater than 0 for some g everywhere in omega, then the set intersection W and U has zero R-dimensional Jordan measure. For preparation of the proof of our statement, we need to break the idea into such parts that in each of these parts, system 1 has one valued solvability. These parts are defined by the maximum minus of the Jacob matrix, the G of the given system. We will break omega into no more than 10 subdomains. Omega nu, as it is done, above which intersect each other only by parts of their borders, and in each of which one of minors of Jacob matrix has maximal absolute values among all minors. In each subdomain, omega nu, the nth minor everywhere accepts maximal absolute values. It is well known that each subdomain is a closed set and can be represented as a union of finite number of one-connected closed domains. Hence, each subdomain allows a representation in the form omega nu is equal to union of subsets omega nu C, where omega nu C are one-connected subdomains. Let's consider one of subdomains omega nu C. In this subdomain, the system 1 is solvable one-valuedly in some neighborhood of given solution with respect to the same variables. Moreover, the domain can be dissected into the union of no more than F subdomains, in each of which the system 1 is solvable with respect, say, the first n minus r variables. Let C is a vector of independent variables. Then it is possible to present each variable as a function. xe is equal to xe of c of independent variables. We will designate by A0 of C a matrix received from the matrix A0 of C by replacement of variables xe by functions xe is equal to xe of C. In other words, we consider functional matrix A0 as a matrix of C. We will designate G1 the minimal value of Graham's determinant of gradients of elements A0 C. Here, differentiation is taken with respect to C. That is, G1 is equal to minimal value of determinant A1 C multiplied by transpose matrix. And here the minimum is taken overall C and V nu. That is why it depends on C. So A1 C means a matrix of the size R multiplied by Rm received from A0 by differentiation on C. It is A1 C is equal A0 prime of C. Thus, the matrix A1 of C, considered as a matrix of C, differs from A1 C because for the getting of matrix A1 of X, we take differentiation of xc, and after we replace variables xe by functions xe of xc, functions of new independent variables xc. But matrix A1 xc is got by differentiation of elements of the matrix with respect to xc. In applications to the estimate of the surface integral or exponential integral, naturally it arises the question on the measure of singularities. We here start with consideration of the set of critical points, that is set W1. Suppose that G1 designates its corresponding maximal minimum. Let P0 be the area of piece delta 1. The proof of our theorem is based on following notice. The set of critical points is defined by the equation with continuous functions. So this set is closed Jordan set. To prove that it has zero Jordan measure, it suffices to show that this set has not interior points. Then this set is consisted of boundary points and therefore has zero Jordan measure. By this reason, assuming contrary, we suppose that the set W1 has inner points. Then it contains some open subset W V. In this subset, we can perform differentiation with respect to independent variables x1, x2, and so on, xr on the surface P1. Denote by ρ1 of xc, so on, ρr of xc, the singular numbers of the matrix A0. Consider the change of variables by formulas. Eta 1 is equal to ρ1 of xc, eta r is equal to ρr of xc, where xc is equal to xc1, and so on, xr. We will analyze the Jacobian of this change of variables. We will show that this Jacobian may vanish only in the subset of zero Jordan measure. For establishing the loss, we at first estimate the Jacobian from below, supposing that it is distinct from zero in an open set. Using this inequality, we prove the main result. Let the system of vectors T1 and so on, Tr of xc and Q1, Qr of xc be singular basis for the matrix A0. Thus, the G of xc belongs to R in power m, Qe to R in power R. We have following inequalities. Every singular number can be represented as a scalar product. Moreover, A0 T G is equal to rho G multiplied by Q G, and A0 transpose multiplied by Q G is equal to rho G T G. If we differentiate the first equality with respect to xc, we get following relation. Partial derivatives rho g with respect to xc is equal to the sum of three scalar products. And using the above equalities, we can represent this sum in the form. It is best known that for every unit vector, the vector is orthogonal to the partial derivative of this vector with respect some independent variable xi. If we use this relation in the above equality, we see that second and third scalar products are equal to 0. So we get the following equality for the partial derivatives of singular numbers. This equality shows that vectors of singular basis behave themselves as a constant vectors when singular spectrum is under differentiation with respect to xi. Then the Jacob matrix of the change of variables can be represented in the view uxi is equal a0 prime multiplied by b, where a0 prime is a transpose Jacob matrix of the system of functions received by an arrangement of columns. A0 consequently at a line as follows. F, E, G are considered as a function of xi, and B is a matrix of the size mr multiplied by r, consisting of columns of tensor product or direct product of vectors T1 by Q1 and Tr by Qr, belonging to the product R in the power m and multiplied by R in the power r. Matrix A0 prime is a matrix of the size mr, so r has r non-zero singular numbers, to every of which is put in correspondence the two system of r orthogonal vectors in r in power r and r in the power mr, accordingly forming singular basis. Singular representation of A0 prime has the form Q prime lambda T prime, where Q prime and T prime are orthogonal matrices of the size respectively R and MR, and lambda is a matrix whose all non-zero elements are singular numbers placed at different rows and columns. We will designate these singular numbers as mu1 of xi and so on, mu r of xi, where the numbers mu1 in the second power of xi are eigenvalues of the matrix A0 prime multiplied by A0 prime transpose. Let's now present inverse value of the determinant of u of xi in the following view. This value is equal to the volume of unit ball in r-dimensional space, where C is a constant expressing volume of the unit ball. Making change of variables, mu is equal to pw. Will present last integral in the form of following surface integral. Inverse value of determinant of ux is equal to, say, in -1 multiplied by a surface integral, where the surface is taken over the surface of r-dimensional subspace. Really, the surface element over this manifold is equal to the square root of determinant of matrix B transpose multiplied by B. Since the columns of the matrix B are unite vectors, then this product is a unite matrix. So determinant is equal to 1. Taking the maximum over all subspaces, we receive an inequality determinant of U of C greater or equal to the product mu1 of C multiplied by mu2 of C and so on, mu R of C, where mu1 greater or equal mu2 greater or equal so on, greater or equal mu R are singular numbers of the matrix A0 prime. Now use Courant-Fisher theorem, which expresses the E plus 1 singular number mu E as follows. Mu E plus 1 in the second power is equal to the following minimum and maximum, which is taken, minimum is taken over all R minus E dimensional subspaces, and U is taken, U runs through all vectors of the corresponding subspace, and R of U is a relation, which is equal to the fraction scalar product of XC to A0 prime multiplied by A0 prime transposed U divided by scalar product, which is the square of the norm of vector U. Now we will notice that A0 C transpose is a Jacobi matrix of the system 1, where differentiation is taken with respect to C. From the theory of implicit functions, it is best known that the matrix A0 prime, it is possible to present in the form D of C multiplied by A1 transposed of C, where A1 of C is a matrix entered above. This is a first derivative of the matrix A0, gotten by the way explained above. And D of X is the following matrix of the size R multiplied by N. Fact known from analysis. The X is a matrix of the form, and it is clear that omega, scalar product omega is equal to scalar product of the transposed U multiplied by the transposed U is form of the matrix D of C, visible that this scalar product can be represented as a sum U plus L0 U and greater or equal to UU, where L0 is non-negative definite matrix of the size R multiplied by R. L0 is equal to the product of matrices, which second matrix is a transpose of the first. From this inequality, we get R prime of U greater or equal R1 of omega. Therefore, we get nu e plus 1 in second power greater or equal minimum over W R minus E at the maximum, where W R minus E means subspaces of dimension R minus E in the space R in the power n, and omega runs over vectors of this subspace. Then the right part of the last equality under the theorem of current Fisher gives n minus r plus e plus 1 eigenvalue of the matrix A1 multiplied by A1 transpose. Hence, the product nu 1 and so on nu r greater or equal Rn minus R plus 1 prime multiplied by Rn prime, where A1 prime, A2 prime, and so on, An prime are singular numbers of the matrix A1. Thus, we have proved an inequality. Determinant U of C greater or equal G1 of C, where G1 of C designates the product of the last R singular numbers of the matrix A1, which under the assumption of our theorem is distinct from zero. Consider now the case of existence of points at which the Jacobi matrix degenerates. Let's show that in this case, the set of points at which the Jacobian vanishes has a zero Jordan measure. Since this set is a Jordan set, then we must show that the mentioned set has not inner points. Suppose contrary, that is, suppose that there exists an open set here in which Jacobian vanishes. Consider the matrix. The zero of epsilon is equal to lambda of epsilon t, where lambda of epsilon is equal lambda plus epsilon multiplied by diagonal xc1 and xcr. This is diagonal matrix containing diagonal elements equal to xc1 and xcr, and other elements is equal to 0. Then we get the 0 of epsilon is equal to the 0 plus epsilon h, where h is a product to diagonal xc1 and so on xcr multiplied by t. Hereby diagonal xc1 xcr we denote the block matrix of the form. Suppose that one of singular numbers of the matrix U of C, say nu 1, vanishes in Y, taking the 0 of epsilon instead of the 0. Let us consider the change of variables. Eta 1 is equal to rho 1 of C plus epsilon xc1, and so on. Eta r is equal rho r of C plus epsilon xcr. The Jacobi matrix of this change of variables is equal u of epsilon is equal u of c plus epsilon multiplied by e, where e denotes the unite matrix. So we have d1 of epsilon is equal to d1 plus epsilon multiplied by h1, where the matrices d1 and h1 are constructed by the way explained before, denoting by m greater than 0 the minimal value of all non-zero singular numbers of uxc in some closed subset y prime in y. Taking epsilon less than m divided by 2, we see that the matrix d1 of epsilon is non-singular. Reasonings made above allows us to note that square root of the determinant of product of the matrices, the 0 prime multiplied by the 0 prime transposed of epsilon greater or equal to J1 prime of u. Here in the right-hand side of the inequality, the product of last s singular numbers of the matrix d1 of epsilon stands. The left-hand side of this inequality tends to 0 as epsilon tends to 0, but the right-hand side remains greater than positive constant. The God contradiction excludes our assumption. So, the set in which Jacobian vanishes has not inner points. Therefore, the change of variables eta 1 is equal to rho 1 of c, and so on. Eta r is equal to rho r of c can have a vanishing Jacobian only in the set of zero Jordan measure. The theorem is proven. Thank you for your attention.